Okay, welcome back everybody. The next speaker is Alessandro Neto. Alessandro is an assistant professor at the Department of Mathematics of the University of Trento. Alessandro is a pure algebraic geometer with a particular interest in applied sciences, in particular questions that come from applied sciences. Today we'll talk about tensor decompositions. We will try to describe some applications while trying to provide us with the theory, the algebraic geometry behind them. So Alessandro, the word is yours.
Okay, so thanks a lot. Thanks a lot for the invitation. It's nice to, I should say, somehow like being back, because I started my bachelor and master upstairs in the math department, but it's nice to be here to give for the first time a talk to a different audience. So my goal today is to talk about tensors. So tensors are basically just multidimensional arrays of numbers. So we have seen in the previous talk that I thank a lot, points, vectors, matrices, and tensors are just multidimensional, multi-indexed arrays of numbers. So tensors naturally appear in applications. That is because, for example, it can be used to describe probabilistic and statistical models. Okay, so I will show some of them later. So, for example, if I pick my multidimensional tensor, I can store inside one entry of the tensor like a joint probability of a bunch of random variables, for example. If I have d random variables, I can store them in a d-dimensional array. So they are also useful not only for discrete data, but also to encode information for more continuous functions. So even if we have statistical models that come from Gaussians that are clearly not discrete, we can store information about our Gaussians somehow and try to understand our models in that way. Or otherwise can just be used to store data very naturally. So we have big data nowadays that vary along multidimensional directions. So here, for example, is an RGB picture that can be stored in a layer of the red channel, green channel, and blue channel. Okay. So why tensor decompositions are useful and what are tensor decompositions? So essentially, it is a way to represent tensor in a convenient way. And that can be used to, for example, find latent structures in our data. For example, we are looking at some data and we don't know if we have some sort of hidden information behind them, okay? And then that can be useful to understand. That can be useful to compress data. It can be useful to classify and cluster your data. And so essentially, these are all higher order generalizations of matrix decompositions. So the matrix decompositions, I guess the most famous, the most used is the SVD decomposition, the singular value decomposition of a matrix. And that can be used to do a lot of things like PCA and many other things to study basically matrix data that are in a matrix structure. Okay, so just a very quick recap of what is a matrix decomposition. So we know what is the rank of a matrix, okay, but this is a different definition from the one that is taught at the very basically in an algebra course. And a rank of a matrix can be viewed as the smallest number R, such that our matrix can be written as a sum of R rank 1 matrices. Okay, so that is equivalent to the usual definition of rank. And here is just a picture of what I'm thinking about. So M is my matrix, that is this rectangular shape box of numbers. And then essentially I can write that as a sum of rank 1 matrices. So rank 1 matrices is just the product of a column vector times a row vector. Okay, that just gives a matrix, a rank 1 matrix. Okay, so my goal is to generalize this definition to the tensor case. Now, I was talking about latent structures. So since we are seeing matrices, I just start from showing you how the rank of a matrix can be used to detect a sort of latent structure. And here is a very, very basic and easy example, but I hope it gives you the idea of what I'm talking about. So let's say that we roll 2 independent dice, and we look at the outcome of those. And then we look at, so of course, for each dice, we have a probability vector, okay, which is they are biased dices. So there is the probability that 1, 2, up to 6. So I have 2 6-dimensional vectors. Now, if I throw them independently, the joint probability is just the product of the 2 probabilities. Okay, nothing special. And that is essentially saying that if I look at 2 independent random variables, the joint probability is stored in a matrix of rank 1. Okay, because it's just the product of the 2 probabilities of the 2. Now, if instead of that game I play a slightly different game, so I throw a coin, and the coin tells me to pick the 2 dice from one bag or another, and then I throw the 2 dice that I find independently. Now I have the joint probability of the outcome depends on a hidden variable that I don't know, because the output doesn't really, I don't know in advance that I have this coin that I'm throwing. And essentially that is what it's saying is that I have this hidden variable that is this throwing of the coin that is essentially telling me that the throwing of the 2 dice is independent conditionally of my extra hidden variables. So for each one of the 2 outcome of the coin, I have a rank 1 matrix. And essentially I'm basically picking a combination of the 2. I'm basically summing them up. So in this case, the joint probability will be a rank 2 matrix. Okay, and then I guess you can see how things go on for a larger case. Any question on these examples for matrices? Okay, so one thing that is convenient is that this is convenient because it allows us to store essentially our matrix to basically is decreasing the storage that we need. So a matrix has n times n entries, okay? And if we write in this format, we are only using r times n plus n numbers, okay? So it's much less. So that's why this is useful. These types of decompositions are useful to, for example, compress things. Okay, so again, this is the usual SVD decomposition that is very famous. It's a way to basically pick a matrix and give us a rank decomposition of our matrix. And essentially, there is this beautiful Eckart-Young theorem that is telling us essentially, so here is a lot of math, but what it's essentially saying is that if I pick my matrix M and I want to approximate my matrix M with a rank R, in this case, what, rank S matrix, okay, the best way to do it is pick the SVD decomposition, keep only the largest singular values, the largest S singular values, throw all the others to 0, and that will give us a rank S matrix, and that is the best approximation of our matrix with a matrix of rank S. Okay? So this is a great result. So essentially, this is a black and white picture, is the rank 1 approximation of a black and white picture. Okay, so a black and white picture is just a matrix. In each pixel, I have the gray scale of it. Then I try to approximate it with slightly larger and larger rank. So if I pick the approximation with this is a standard SVD, rank 5, rank 10, rank 25. Maybe people are starting to recognize what it is. Then rank 50, 100, 200, and now I don't think that at the last row you see any difference if I start to grow up like this. Okay? But it's clear that the rank is getting bigger and bigger, right? So the original one at rank 853, but actually I can approximate it pretty well with quite smaller rank. Okay, so this is just a very easy example, but if you imagine if you have like a very big data can be, data set can be useful. So matrix decomposition is a method in 2 dimensions for matrices, but can be used also to approximate tensors, which are multi-dimensional things. So the idea is that if I have a color picture, okay, so I have the 3 channel R, red, green, and blue. But one thing that I can do is pick every layer, I perform the SVD there, and then I put everything back. And this gives us an approximation of our original data with smaller storage information, essentially. Okay, is it clear? Yes.
Just one question. When you say that you divide things and then you put them back together, but still, I mean, you have the RGB things divided.
Yes. So essentially, at the end, like after the SVD, is like approximating the red with another red, the green with a green, the blue, and then I summing them up.
Yeah.
Or like putting them back to a.
Yeah. No, that's exactly what I was thinking. So you're not like summing them to a construct like the RGB image.
Yeah.
Okay. So you basically you still keep the layer.
Yes.
Also
Yes.
like, okay.
Yes. Exactly. Thanks. Yeah. Okay. So this is again like the same game as before. Okay. Then this is the rank here that I'm putting up there. Is the rank that I'm using in each SVD in each layer. Okay. And again, just more or less the same game as before. Now, the concept now is the following. So I used a method that is thought for 2-dimensional things, and I'm using that for multi-dimensional things. Okay, that can be useful, but maybe we can even do better. So tensors are multi-dimensional. So we should find, or we should try to use methods that in the method they keep or they exploit the multidimensionality of our data set. And that is why tensor rank decompositions are coming. So essentially, again, up there is again the definition of rank of a matrix that I gave you before. Okay? What I want to do now is essentially giving you a definition of rank 1 tensor. And then essentially I'm just considering the composition of my tensor as sum of rank 1 tensors. Okay, in the same way we do for matrices. Okay, so this is my mathematical setup. Okay, but previous talk we already talked about vector spaces, so I'm very relaxed. So here, basically, in the case of matrices, I can look at V and W. Whenever I write V as just a vector space over a field, I have dimensions of these vector spaces, and I have bases for them. Okay, so for the ones that remember vector spaces and what it is, okay. Otherwise, just think of V and W as R to the N or R to the M, or C to the N, C to the M if you prefer complex numbers. Okay. Okay, so the tensor product space V tensor W, okay, is basically the space that is generated by the tensor product of the 2 bases. So essentially, the EI tensor EJ there is the basis that is basically picking the entry IJ of my matrix. So here in the bottom, a matrix is essentially a combination of these entries that is essentially saying that in the IJ entry of my matrix, I have the number Mij. Okay, so this is matrices. Now, again, this was the thing that I said before. What is a rank 1 matrix is a decomposable matrix in the sense that can be written as a tensor product of a vector in V and a vector in W. Okay? And if I do that tensor product by using linearity and so on, basically here what I'm saying is that at the entry ij, I have the product of the ith entry of the first vector times the jth entry of the second vector. It is exactly what we had before. Now, let's generalize everything. Essentially, I'm picking D vector spaces. D is basically the order of my tensor. Okay, so the number of indices that I am moving from. And so essentially, again, here at the bottom, we have that a tensor can be written as a combination of those of that basis that essentially is telling me that in the entry of the tensor indexed by I1 up to ID, I have the number T I1 ID. Okay, so exactly in the same way of matrices. Now, what is a rank 1 tensor? Well, it is gonna be just a tensor product of a bunch of vectors, one for each vector space that I have. Okay? And again, I use multilinearity and everything, and if here I perform this simple algebra computation, this is telling me that this rank 1 tensor in the position I1 up to ID has the product of the elements of my P vectors, where I multiply in the first one, I pick the I1 entry of that, up to in the last one, I pick the ID entry of the last one. Okay, so it is exactly the same thing as for matrices here, just in a multi-dimensional, in a multi-order space. Okay, now back again on a statistical. Yeah.
Just one thing.
Yeah.
So basically, the right part is just basically creating the space.
Yes.
So like D1 times D2 times D3 times D.
Exactly.
And the first part is because I lost like EA coefficients.
Yeah. So so essentially, what I have here probably I have that the vector v1. So this one here is the vector v1.
Yeah. Okay.
So these are the entries of my first vector.
Okay. So
these are the entries of the set of the last vector, and these are just the e's are the bases.
Yeah, exactly. So basically, it's just like the last part is just the multiplication of like constants.
Exactly.
Then you have, okay, so
this is just a number.
It's like m, for instance.
Yeah.
Multiplying like all of the things.
Exactly. So, for example, if I pick, this is just a very easy example, but if I pick, for example, this vector here, this tensor product. Okay. So this is going to be a 2 by 2 by 2 cube. Okay. In the 1, 1 entry, what I put up here is going to be the product of the first entries.
Okay, clear.
Okay. And then I just do the same. Yes. Basically, I'm moving on this cube. I'm just changing the kind of indices that I'm picking in this part.
Yes. Basically, it's the pairwise of the pairwise, let's say.
If you want or something. Okay.
Thank you.
Yes. So essentially, the indexes that I'm moving here are just telling you which entry you have to pick for each vector. Okay. Thanks. All right. So back on probabilistic type of view of tensors. So again, rank 1 tensor are gonna be essentially the model for independent models. Okay, so they are the object that are storing independent models. Again, because if I have a bunch of random variables and I look at the joint probability, I store that in a big order tensor. Okay, saying that is a rank 1 tensor is saying that it is essentially the product of the vectors describing the single probabilities of my single random variables. Okay, so essentially, linear independent random variables correspond to rank 1 tensors. All right, so now we can move up and we can pick combinations of rank 1 tensors. So a tensor is going to have rank R if it can be written as a sum of R rank 1 tensors. Okay, so this is again the same definition as for matrices and just having more modes, if you like, in that term. Okay, and the smallest possible, so the minimal length of such a decomposition is what we call the rank of the tensor. Okay, and this is going to be a tensor rank decomposition. But if you want to Google it, you can find most likely in more applied sciences canonical polyadic decomposition, okay, or CPD. Okay. Now, again, what we want to do is we have our tensor, and one question could be, okay, can we find what is the best approximation of my tensor with a tensor of low rank? In the same way as the SVD was telling us what is the best rank R approximation of a matrix. So essentially what we want to solve is this problem here in yellow. So finding vectors to put in my sum up there in order to find the best rank R approximation of my tensor T. In the same way we're doing for the SVDs. Now there was a beautiful Accordion theorem for matrices. Unfortunately, for tensors, this optimization problem might have not a solution. Okay, there exist tensors for which we cannot get an optimal solution of this optimization problem. And that is a big problem, of course, but is giving geometers job. Okay, so I'm trying to giving you the motivation of this fact from a geometric perspective. So the idea, again, for matrices, why it was working the Accordion theorem essentially is because if you pick a family of matrices depending on from one parameter, and all of those matrices have rank R, also the limit is going to have rank at most R. Okay, so if you pick a limit of matrices that have rank 3, okay, at the limit you cannot get matrices of rank 4. Okay, the rank is keeping, because essentially the rank is given by the vanishing of the of a bunch of minors of your matrix, and of course that vanishing is also be true in the limit of that. Okay, so this is essentially why everything works there. Now for tensors, this is not going to be the case, and here there is an example. So essentially, if I pick the set of tensors of rank at most R, that is not closed. So if I pick here in blue a rank 3 tensor, okay, this is living in C2, 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 or R2, R2, R2 if you want. That rank R tensor can be written as a limit of that sum. And if you look inside the brackets, that is a sum of 2 rank 1 tensors. So I'm seeing that as a limit of rank 2 tensors, and I jump up to have a tensor of rank 3. Okay? Geometrically, what I have is essentially this picture. So this surface is the space of rank 1 tensors. Okay? Now, if I pick a line connecting 2 points there, and if I pick here like an orange point, that is a combination of these 2 points. So this is going to be a rank 2 tensor, right? Because it's a sum of 2 rank 1. Now, the idea is that I can move like this secant line, okay, up to the tangency, right? Like a tangent line is a limit of those secant lines. And what's happening is in this process of limit, like this geometric idea of going from a secant to a tangent, this limit at the end is going to have rank 3. And that is why tensors are bad from one point of view, but I will also try to tell you that also tensors are very good for many other things. So essentially, this is giving the reason of defining what is the border rank of a tensor, which is essentially the smallest R for which I can approximate, or I can actually view my tensor as a limit of rank 1 tensor. Okay, as I'm saying, this guy here has rank 3, but has border rank 2, because I can see that as a limit of rank 2. For matrices, there is no need because everything is closed, so at the limit, everything goes fine. So that's why we don't teach border ranks of matrices, because there is no need for that. Okay, so this is a picture essentially of what I'm again trying to say. So imagine we have our tensor T, and we want to approximate that, find the best approximation with a tensor of rank at most R. What is happening is that in this space, so the best approximation would be this point here in the middle, this point here in the middle would be like geometrically the best approximation. But what's going on is that as long as I approach that, I stay with tensors of rank R, but at the limit that jumps up. So if I want to find the optimal rank R approximation, I basically should go up here, but when I arrive there, I no longer have a rank R tensor, I have something of much bigger. Okay, so that's the problem. Okay, so there are anyway iterative algorithms to find anyway some good rank R approximation. Okay, so that is the best doesn't exist, but there are like good ones that can be solved by optimization problems essentially. And just one, so that is implemented, for example, in MATLAB. There is a package called Tensor Lab that has stored all these kind of objects. There is also a Python library now, Tensorly or something like that. I have never used that. It's pretty recent, and I don't want to talk about that, but I think it's pretty good, but I never used it. So one, for example, just to give you an idea of what could be like a very good way to try to approximate this thing, is essentially, for example, trying to solve this optimization problem mode by mode. Okay, so you start from your tensor. Okay, you fix all the modes but one. So essentially, you fix all the directions but one. So essentially, you're looking at matrices. You approximate that by using the usual alternating least squares or whatever. You approximate that. And then you start to fix that, and you start to look at another mode, then you approximate that one, and then you go to another mode, you approximate that one, and you keep going this way. Okay. So that is one way to, for example, there are other algorithms, but this should give you an hint of what's going on. Okay, so what I'm saying here is the following. So this is an example. So I started from my RGB color picture, and one thing I said is, look at the three channels, red, green, and blue, do the SVD there, and put it back to a picture. Or what I can do is to decompose that already at the tensor level, okay, finding a good rank S approximation of that in terms of rank, and then getting again the tensor that comes up. Okay? And I want to compare with you, like a moment, the outcome of these two guys. Now, if I look again, as before, if we look at the first part, so decomposing by SVD each one of the channels, the storage, the cost that I need is this number. It's 3R times n plus n. Okay, so I have n plus n in each summand. I have 3 of them, and I have R summands. While if I use the CPD decomposition of rank S, the number is now this one, is S times R plus n plus n. Okay, because for each summand, I have 3 plus m plus n. Okay? So this is telling me is that if I want to compare the two methods, I should not use the same rank. Okay? But on the tensor level decomposition, I can use a much bigger number than the one that I was using for the SVD. Okay, so S, in order to compare these two, S should be approximately 3 times the rank that I'm using also. And this is for you the outcome that I have if I look at the matrix decomposition in each layer, and then I put it back by using rank 18, versus the tensor one if I pick rank 50, that is approximately 3 times that. Okay, and for sure, from the last row, it should be clear that the one on the right is a bit better than the one on the left. Okay, so essentially, this is telling us that even when we have like big data, multi-dimensional, this is just one example, it can be good to decompose, to try to find a composition at the tensor level, try to compress it from the tensor level without losing the tensorial structure of that. Okay? And here I'm also saying that I'm also showing you one example of tensor decomposition, but there are many others. For example, higher order circular value decomposition that are slightly different and so on. Okay, so but for a matter of time, I can only talk to you about one. Okay, so I just want to give an hint again on statistical models. So again, we said before that independence models are basically stored in rank 1 tensors. Mixture models are stored in rank R tensors. Okay, mixture models is essentially saying that they look at a bunch of independent variables conditionally to an extra variable. Okay. And so the joint probability is going to be essentially a sum of probabilities depending on the outcome of the hidden variable. Okay. So if the hidden variable adds R states, then I have a sum of R. I have R sums. Okay. So usually this is this kind of statistical model I draw in that with that graph down there. That's essentially saying that the bottom layer is independent conditionally to the one upstairs. And well, of course, I can add more hidden variables. Okay, for example, machine learning, there is restriction Boltzmann machines that are essentially the starting sort of building blocks of deeper networks. So it's just basically just one part of it. And I have, for example, here I have a bunch of independent variables, the bottom layer, that are independent conditionally to the one upstairs. And I also assume in the vice versa. And in that case, I can represent that joint probability on the visible layer by the Hadamard product of rank R tensors, where the Hadamard product is just the product that every high school student would like. So it's just the product of entry-wise product of tensors in this case, okay, without row and columns. Okay, this was just to say that tensors can be used to represent all this kind of statistical models. Now, what algebraic geometries do? So I'm talking now about statistical models. What are statistical models? They are tensors whose entries are real numbers because they are probabilities. They must sum to 1, and they must be all positive and so on. So I have a lot of conditions there. Algebraic geometry is the field that is studying sets of solutions of polynomial systems of equations. Okay? We only study sets that can be represented as solutions of polynomial equations. And when we introduced complex numbers was essentially in order to be sure that every polynomial had a solution, right? So in order that x squared plus 1 had a solution, that was giving us the fundamental theorem of algebra. So algebraic geometry usually works over the complex numbers. So that is the place where algebraic geometry works. So what we do essentially is to pick this statistical model, we extend it to an algebraic model in the complex numbers. So basically we drop out all these conditions downstairs, and we study that algebraic model up there. Okay, so for example, the rank R complex tensors and so on. There, what we do is we use algebraic tools to study, for example, dimension of those geometric objects or equations defining that geometric objects. The good thing is that these features of our geometric objects in the complex space is useful also to understand down here. Why so? Because the dimension essentially saying what is the optimal number of parameters that you have on your model. And the number that you get in the complex, well, is essentially the same that should be in the real, because this is just intersecting the bigger object with the probability simplex, if you want. Okay, you can see the probability simplex where this is living embedded in the big complex space, and I'm just studying the big complex geometric objects. Okay, here I just want to intersect it. Also equations. Okay, so if I'm requiring that bunch of tensors with some property needs to satisfy some equation, of course, also this one must satisfy the same equation. Okay, but there I have algebraic tools to study those. Okay. So that's why it is useful. Of course, here there is much more. There are all the inequalities because of the positive. I want to real numbers and so on. So that is not the end of the story when I move back here. I'm not saying that we solve everything, of course. But that can be useful. Okay, that is how, for example, when we talk about algebraic statistics, this is the concept that is behind this. Okay, so when did we start? I don't remember how much time was.
I think you still have 15 minutes.
How much? 15?
15 minutes.
Okay, so let me skip for a moment this, even though there is a beautiful picture of an old Italian mathematician. So at the beginning, I said that tensors can be also useful not to study only discrete models, discrete random variables, but also continuous ones. So, for example, Gaussian models. Okay. So here I'm going to give you like an example of that in order to let you understand what I mean. So again, as I said before, rank decomposition is useful to understand latent structures in our data set. So this is an example, a very famous example of Pearson in the late 1800s, that he was studying the data on the dimension of crabs. Okay, and essentially here you see like the blue diagram is essentially the ratio between the breadth of the forehead of the crab over the body length. Okay, so it's basically storing the shape, the quotient between the shape of the crab. And then, of course, you see that this blue shape here of the data is very much not the Gaussian. I mean, it's very moved on one side. Okay? And here he's saying in his paper from that time that the asymmetry may arise from the fact that the units grouped together in the measured material are not really homogeneous. So essentially what he's saying is that inside this population of crabs, there are actually two subpopulations that behave corresponding to two different Gaussian models. So this, you see the idea is that you have a red Gaussian that should be the one corresponding to one population and the green Gaussian corresponding to the other population. Okay? And putting that together in a mixture model should be the blue one. So essentially the goal is to understand this kind of facts. And so the idea is that now if we assume that we have these two populations going with two different Gaussian models, the probability distribution is the mixture of these two Gaussian models. So I'm just summing them with this alpha that is basically saying is an attribute to the percentage of one subpopulation with respect to the other. So the identifiability problem is essentially saying, can we find parameters, mu1, mu2, sigma1, sigma2, and alpha, that such that this P, this model, approximate well the frequencies that we have in our data sets. And so that is the kind of goal of this kind of identifiability problem. It's trying to identify the parameters of the model that best describe our data. Now, Pearson's idea was to use moments. So he introduced the method of moments. So the ith moment is essentially the expectation is the power of the variable, so it's that integral there. And if you do that computation on a Gaussian distribution, you can see that these are the kind of output that you get, depending on mu and sigma. If you see here, they are all polynomials in mu and sigma. Algebraic geometers are extremely active because we can give a help to study this kind of objects because it's a solution of polynomials. So the idea is to essentially compute the empirical model, empirical moments from the data set, compare with this one, and try to solve those partial equations. Okay, and that is what we can do with cumulative algebra methods and computational algebra. Okay, so assume that we don't have only one variable, but we have many of those. Now, the idea is that we can build up tensors that are called the moment tensors. So, for example, the kth order moment tensor is a tensor in which, in the position I1 up to Ik, I get the expectation of the products of my random variables, where I'm picking just the one that are corresponding to the indexes that I see. Okay. So, for example, if I have two. If n is equal to 2, then I have that the first order tensor is just this vector. The second order tensor is the symmetric matrix, where I have on the diagonal these two entries and on off diagonal this number here. Then I can use the third order tensor, is just a three-dimensional tensor, and so on. Okay, I can do that for arbitrary I k. Analogously, we can define what is the kth order cumulant tensor. That is something that is coming up again from the moment. This is the mathematical formula, but essentially this is saying the following. So I'm summing up over all the possible partitions of the k indices that I have. Okay, so I fix a partition of that numbers from 1 to k. That partition, I'm basically picking the expectation of the products of the variables corresponding to that partition, and then I'm putting everything up. In the case I have variables with mean equal to 0, this simplifies a lot, and I just stop at the third order tensor. So this is the first order tensor that is again at the entry I. This is a vector that has in the ith entry the expectation of the ith variable. The second order cumulant is a matrix where I have the expectation of xi, xj, so the covariance matrix. Then I have the third order tensor, while the fourth order tensor is starting to be a bit more fun. Okay, I have more components. I have this expectation here where I have to subtract just these partitions, because with this assumption, essentially, since this guy is the mean, all the other types of partition have one element, so everything goes to 0 because the expectation is equal to 0. So that's why these are the only partitions that remain. Okay. Okay, so basically I built up tensors from my Gaussian models. So I want to apply this to a problem that is usually called the Cochlear problem. So imagine we are in a room with n people talking and n microphones put it in places. Okay? And then I have basically what I get is this matrix equation where in the ith row of y, I have the signal from the ith microphone. Okay. In the ith row of x, I have the signal produced from the ith person, and M is just a matrix that is describing the superposition that I have in the ith microphone, the kind of signals that are summing up from the signals from the people. Okay. So the goal is, can we recover x starting from y? Okay, I will give you data y. So I will show you in these examples. So my signals will be just 4 pictures that are the result of 4 pictures summing them up. Okay, so the people are 4 pictures that I want to recover, and the signals, so the microphones, are just these 4 pictures that are a combination of the them. I don't know if you recognize already something, maybe or maybe not. So the goal is to see what will be the outcome. So can we recover x? No, the problem is not identifiable. If I just think about this in terms of matrices, it is definitely not identifiable in the sense that in the middle of this product of matrices m times x, I can always put the identity. And for every invertible matrix, I essentially can place instead of the identities just A inverse times A. And then this m times x is equal to some other m prime x prime. So there is no way from this matrix approach to recover the signal because I have a lot of possible solutions. So matrices are not helpful here. So the idea is the following observation is the properties, algebraic properties of cumulant tensors. So essentially it's the following. So signals are independent random variables, okay? And this is the fact. The kth order cumulant tensor is diagonal. When I say diagonal, I'm saying that the only entry that are different from 0 in that tensor are the ones that have indices that are all the same, in the same way as the diagonal of a matrix. okay? Just on a tensor. So it is diagonal if and only if these are statistically independent. Okay? So this means that my cumulant tensor here has a unique expression in this sum. Okay? This part here is saying that I have to put lambda I in the position I, which are the only ones that are different from 0. All the rest is equal to 0. Okay? Now the facts, and this is again linear algebra, if T is that combination of my signals, okay, essentially what I get is that the cumulant of that T is again something diagonal, but instead of having the standard basis, that is the one that I had down there, essentially here I have the ith column of my matrix M. That is the one that I had from the one of the things that I want to understand from the problem. So this is great because I want to stress this thing, which is why tensors are amazing. Tensors are in general identifiable. So matrices are not. Again, this is the problem. Matrices, you can always do something like that, and it's not identifiable. Tensors are. Well, not every tensors, but with probability 1 they are. So in most cases, we are fine. So essentially what it's saying is that if we want to compute the source x from the signals y, what we have to do is construct the fourth order cumulant tensor from the signal data, compute the tensor decomposition of this tensor y, and that gives me M, because it's giving me this tensor decomposition is giving me the columns of my matrix M. Okay? And then once I have M, it's easy to prove that that is going to be also invertible. I just from the equation mx equal to y, I'm just inverting everything, and I get that x is equal to m inverse times y. Okay? And so if we pick this data set, essentially, what we build is that our matrix that we build is putting, like, vectorizing each picture. Okay, so I have a matrix that has 4 columns because there's 1 for each picture, and then I'm vectorizing all this stuff. But then I'm basically tensoring everything back because I construct the cumulant tensor and I decompose the cumulant tensor together. And then the outcome is this, that I guess you can recognize at least 2 of them. The rest is from Trento, so I'm affiliated in Trento. I am from Genoa, so that was a great example for me. Okay? Okay, any questions on these ideas? Okay, then I want to conclude with another question that I think is great because it's one of the questions that we were seeing in the previous talk at the end. So I'm asking, what is the complexity of n by n matrix multiplication? Okay. So the usual matrix column multiplication has complexity n to the cube. And that is because for each entry that are n squared, I essentially have to do n multiplications. In 1968, Strassen wanted to prove that at least in small matrices, that is the optimal complexity for every algorithm to compute, to perform matrix multiplication. That was his goal. He failed completely, but he failed in an amazing way, because by failing, he found a better algorithm and essentially proved that the complexity is actually at most that n to the 2,81. Okay? Okay, so essentially what he did is the following. So if I want to multiply these two 2x2 matrices, the thing that I have to do are those 7 multiplications and then putting them in the correct position there. Okay, so this is, instead of having 8 multiplication, it has 7 of them. Then, of course, I can iterate this thing. So if I have n by n matrices, I can divide them in blocks that are more or less n², and then I perform this algorithm over and over again. And essentially, this is saying that eventually the complexity has this log 2 of 7 up there. That is that number 2.81. Okay, then why this is related to tensor decomposition? So this is again tensor decomposition. Why? So matrix multiplication is a linear map in the sense that it's picking a 2x2 matrix, another 2x2 matrix, and it's cooking another 2x2 matrix, which is bilinear, okay, in the entries of the matrix. Okay. Now, what I want to convince is that that is actually a tensor, because it's essentially this tensor here. Okay, this because the essentially the HK. So here you should think that the first and the second vector spaces are the vector spaces where A and B lives, while the third one is the one where C lives. And this is essentially saying that in the HK position, I have the summation along the jth entry of A and B. So I'm multiplying rows by columns. Okay, so this essentially is the usual matrix multiplication in the vector times column way. And if you want, you can also view that in the following way. So it is a trilinear map that is picking the free matrix is ABC and is giving the trace of that. Okay, so this is a fact that is always true. A tensor can be always viewed as multilinear functions and vice versa. So if you have a problem that is involving multilinear functions, you can always place that in a tensor, and maybe you can study the tensor there to understand your function. So of course, this is going also for n by n matrix multiplication, which is just a tensor in Cn squared times Cn squared times Cn squared. And essentially what is going on is the following. So if omega is the best exponent of an algorithm to compute, of the complexity of an algorithm to compute matrix multiplication, then Strassen proved that that omega up there is also the asymptotic behavior of the ranks of matrix multiplication thought as tensors. Okay? So imagine that you have all those Mn tensors that are all these guys here. And as long as I increase n, I look at how the rank is increasing. That is the same asymptotic as the complexity of the matrix multiplication. After that, even better, it's not just the rank, it's the border rank of that, it's the behavior of the border. So the border was that limit process. Okay? So essentially, this is again a geometric problem, because I'm just saying I pick those tensors and I want to understand over which object that now is closed, because if I look at border, it's just thinking of the honest closed thing. And I want to understand the rank of that tensor there. So what are so far the results? And in 82, there was this great result from Cochlear and Vinograd that went down to 2.37. Then there has been a lot of work, even very, very recently. But as you can see, we are not moving that much, okay? But still, okay, so there is a lot of work there. And so essentially here the question is, can we go down to 2 plus epsilon, okay, for every epsilon? And if we can do that, essentially what he's saying is that for very large matrices, the product is the same as the sum, okay? Because that number 2 is the complexity of the sum, right? Okay, so this concludes this example. So take-home messages. Data naturally are multidimensional, and they are naturally stored in tensors. And so tensors is a way to store data or multilinear maps. Or before we saw, again, when I'm saying multilinear maps, it's the same thing as in the previous talk. We were basically storing in a matrix a transformation of the space. Okay, it's exactly the same thing I'm saying here. Tensorial method exploits such multidimensionality when studying this kind of data. And that can be extremely good for compressing, denoising, searching for hidden structure, and many other applications. Again, I just talked about one tensor decomposition that is the best one because that's the smallest number of summands, but there are other types of decomposition that can be useful for other types of problems. And statistical models and statistical structures that depends on polynomials from the parameters of the model, okay, so that can be described polynomially in terms of the parameters, can give hope for extremely fruitful collaboration between algebraic geometers and applied scientists, okay, so in the two directions, okay, you can tell us what we should try to do, okay, and we can try to give our contribution to it. Okay, so if I manage to convince you that tensor decomposition are interesting and good, next month we will have a master class. It's going to be of just 5 lectures, 2 hours each, and from the 8th to the 17th, so it is spread out the weeks. Is advanced master level or PhD level, but in case you might be interested, just send me an email and see. So with that, okay, I don't have a thank you slide, just stop here. Thank you.
Thank you very much for the very interesting talk. So we're running a bit late, but if you have some questions, maybe. Okay.
So, yeah, okay, so I'll just pick few of them, not all of them there.
You can write me, please.
Yeah. So, first one is just a curiosity. So at the beginning, you basically you do images and then you decompose it like with SVGs, and then you show that with either with SVG or either with the rank, and then you see like varying the rank, how much detail you record and use. And then you can do the same thing with tensors. So my question is how that can be similar or not to something that involves also Fourier transforms. If I have an image, I have a very, very clear idea on how to do Fourier transform. I mean, the Fourier transform on that to compress or decompress the place. Is there is something similar in the tensor world or not?
The honest answer is that I'm not sure, and I don't actually know. It's from the top of my head, I don't. But it might be. Okay, but yeah, I mean, I don't have a very quick question. So yeah.
Because when you see like some of things was like, I mean, maybe I'm biased, but I was thinking like
Yeah. No, but I mean, it's, I mean, also I'm saying like, I mean, I'm not claiming at all that these are the best way if you want to compress pictures and so on. I mean, it was just to give a very specific example that could be useful to understand the topic. But yeah, I mean, I don't know.
Okay. The second thing was, so you showed us like I take like one image, then decompose it. So since we are dealing with tensors, I had one dimension, and like the dimension I'm adding is the number of images. So I can do the same decomposition for like a data set.
Yes, exactly. So essentially, that is the idea. I mean, if I have a data set that has a lot of dimensions, whatever they are, so a lot of indices, then one thing that one can do is to try to compress is just picking like this CPD decomposition of the whole tensor. And there are also ways to say that you want, for example, to classify your data set somehow with respect to some direction. Okay, so I mean, if I pick the usual MIS data set with the number, everything like that, then I can write, I mean, I can store everything in a giant tensor, but then I want to classify the direction of the numbers. Okay. So the idea is that I can find good decomposition of that essentially is compressing all the modes by that and not that one. So it's compressing all the other modes, but keeping all the 10 of them, and somehow giving what are the correct directions where I should project a new unwritten. So in similar way as you do for PCA, where you pick like the good components where you want to project,
Okay.
and you can do something like that also.
With samples.
Yes.
Okay. And last, you can have different decomposition. So if I have like n dimensions, I can have like different quality of compression, let's say, for different dimensions, or I should, use the same level for everything. I don't know if the question makes sense.
No, it makes sense. So no, I can also compress. I mean, the different modes can be compressed in different ways or using different numbers.
Okay.
And that depends a lot on. It depends a lot on what kind of problems you want to. I mean, if you just want to, compress no matter what, maybe you use the same number for all the modes.
Mm-hmm.
But maybe, as again, if you want to prefer one direction, maybe on that direction you don't want to compress, you compress all the rest.
Okay.
And but again, the good thing is that the fact that you don't have an optimal solution, that was the problem that I was saying in the beginning, is giving us like the fact that we can approximate in many different ways. Because anyway, we don't find the optimal one. Okay. And so depending on what is the problem, what is your data set, what you want to do, maybe you can choose different types of decomposition and so on. Okay. Thank you.
Okay, maybe just another question there is. Okay, let's back to the speaker again. So the workshop ends here. So thank you very much for coming. Thank you very much for the speakers. And hopefully next year will be bold in presence, few presence. And thank you very much.
No.